Hello my friends and welcome back to the You Can Do TV channel. The construction of the longest embedded piles in Korea, reaching a depth of 62 meters, was completed using the innovative double machine auger (DMA) method. This project took place at 380 Songdo-dong, Yeonsu-gu, and utilized specialized techniques to install steel pipe and PHC, pre-stressed high-strength concrete, piles. The DMA method, involving two drills working simultaneously, ensured efficient drilling, casing installation, and the placement of composite piles. The construction process began with the preparation of the composite pile, followed by drilling and the insertion of the lower casing using the first drill. The pile structure consisted of a 2,500 mm diameter steel pipe with a thickness of 12 mm. The composite pile was made up of different sections. The top pile measured 7.0 meters, while the lower and middle piles were both 15.0 meters long, and another section was 10.0 meters. As the process advanced, a second perforator was deployed to assist in the insertion of the casing and the perforation of the soil. These sections were horizontally welded together, forming a 62-meter-long HCP composite pile that provided the required strength and stability for the project. In the next stages, both screw rods were extracted in sequence, first the upper screw rod by the second perforator, and then the lower screw rod by the first drill. This step allowed the insertion of the HCP composite pile. The use of the DMA method, with its dual drill approach, enabled precise placement and reduced time for casing and pile installation. This method proved crucial for constructing such deep, embedded piles, setting a new benchmark in Korea's construction industry. Once the pile was positioned, the casings were extracted in reverse order. The upper casing was removed first by the second perforator, followed by the extraction of the lower casing by the first drill. The final stage of the process involved verifying the penetration of the pile to ensure it had reached the intended depth and was securely embedded. Dongram construction utilizes the SHS method, an advanced construction approach that integrates the advantages of shield tunneling and open-cut techniques for underground structures. This method minimizes the impact of environmental conditions, allowing construction even under challenging conditions and in areas with complex underground structures. It's up to 5 times faster and safer than traditional divided installation methods, delivering economic efficiency and reducing costs as the project length increases. In the past, the sliding method required repeated installation and dismantling, causing significant traffic disruptions. However, Dongram Construction's SHS technology minimizes these disturbances and ensures safe, rapid project execution. The SHS method eliminates risks associated with confined spaces by establishing a single frame along the entire length of the construction area, resulting in a highly secure work environment. The SHS process follows a series of structured steps, including assembly, forward movement, backfilling, and installing PC conduits with internal and external finishes. This repeatable process prevents ground subsidence and avoids vibrations, making it ideal for densely populated areas, schools, hospitals, and areas where minimizing traffic interference is crucial. There are two main types: the standard SHS method and the SHST method, which is suitable for deep and complex areas that require the avoidance of specific underground installations like gas or water pipelines. The SHS method begins with the assembly of pre-constructed 1.5 meters to 6 meters wide PC conduits, suitable for medium to large-scale applications. The cylinders expand to move the frame forward, removing soil with a vacuum excavator. With every forward push, the backfilling space is filled using the excavated soil to prevent collapse, stabilized by rubber panels to seal off the area. Subsequently, the PC conduits are inserted, secured with steel tension rods to remove any gaps, followed by the addition of concrete anchors every 3 days for firm stability. After the conduits are aligned and secured, silicone and additional seals are applied to ensure a durable, waterproof finish. The SHST method, with similar components, is employed for deeper construction zones where obstacles like gas and telecommunications lines exist, providing a more economical and environmentally friendly option than traditional slide methods. By establishing a single installation that allows work across an entire project section without vibrations, Dongram construction minimizes public inconvenience and reduces complaints. Constructing a railway tunnel using a tunnel boring machine, TBM, is an advanced and precise method for large-scale infrastructure projects. The TBM, with a diameter typically ranging from 8 to 12 meters for railway tunnels, is deployed to bore through varied geological conditions, including soft soil, hard rock, or mixed terrain. It moves forward at an average rate of 10 to 15 meters per day, though in ideal conditions, it can reach up to 25 meters daily, minimizing construction time significantly over traditional methods. As the TBM progresses, it simultaneously excavates material and installs precast concrete segments, which are typically 1.5 to 2 meters long with thicknesses of 30 to 40 centimeters. Each segment is carefully designed to interlock, creating a stable, reinforced ring that supports the tunnel walls and resists high pressure from surrounding earth and groundwater. A complete ring usually comprises 6 to 9 segments, and every ring extends the tunnel length by 1.5 to 2 meters. The segments are equipped with rubber gaskets and are bolted together to ensure a watertight seal, critical for tunnels located below the water table or in areas with high groundwater levels. Concrete segments are fabricated off-site to maintain quality and transported to the TBM location for installation. The reinforced concrete ensures a lifespan of over 100 years, accommodating the heavy loads and vibration typical of rail traffic. Producing tunnel segments for tunnel boring machine, TBM, tunneling projects, such as those in Abu Dhabi, requires careful adherence to specific processes. These segments form the structural lining of the tunnel, which must withstand high pressures and environmental conditions. The production process begins with preparing the molds used to form each tunnel segment. Production of reinforcement cages. Reinforcement cages are vital for enhancing the structural strength of each segment, especially under the immense pressures typical of tunneling environments. Fixing the reinforcement cages. Steel cages are assembled and securely placed inside the mold. These cages are often tailored to the specific dimensions of the tunnel segments and are crucial in resisting tensile forces and minimizing cracking. Closing the mold. After positioning the reinforcement cages, the mold is closed, ensuring the cage remains in its designated position during casting. Concrete production. Concrete used for tunnel segments requires precise mixing of ingredients to achieve specific properties in terms of strength, durability, and flexibility. A typical mix for tunnel segments includes the following components: Dune sand and washed sand. Both dune and washed sands are added to the mix to create a uniform texture and add strength to the concrete. Dune sand provides flexibility, while washed sand ensures cleaner, higher quality concrete. Gravel. Gravel adds bulk and improves the compressive strength of the concrete, allowing it to withstand high loads. Steel fibers. Steel fibers are mixed into the concrete to improve its tensile strength and enhance resistance to cracking. They are particularly useful in segments designed to withstand high pressure and high moisture environments. Fresh concrete tests. Freshly mixed concrete undergoes quality control tests, including workability, slump, and air content tests, to ensure consistency and adherence to design specifications. Casting of the segments. Once the concrete mix meets quality standards, it is ready for casting into tunnel segments. Casting. Concrete is poured into the prepared molds, filling every cavity around the reinforcement cages. It is vibrated to remove air bubbles, ensuring the segments are solid and uniform. Finishing the segments. After the concrete is poured, the segments are leveled and smoothed to achieve the required surface finish, minimizing imperfections. Curing. Proper curing is essential to achieve maximum strength in the concrete. Segments are usually kept under controlled humidity and temperature conditions to prevent cracking or premature drying. In some facilities, a steam generator accelerates curing by providing warmth and moisture, allowing segments to reach the required strength more quickly. Concrete lab. Each batch of concrete undergoes laboratory testing to ensure that the segments meet the specified quality and durability requirements. Chloride migration test. This test assesses the concrete's resistance to chloride penetration, an essential property for structures exposed to moist, saline environments, such as tunnels near coastal areas. Compressive strength test. Samples are subjected to compression to ensure the concrete achieves its target strength, a critical factor in the overall durability and safety of the tunnel segments. Steel fiber beam test. Since steel fibers enhance the segment's toughness, this test evaluates how well the fibers perform under load, particularly in terms of resistance to cracking and bending. Demolding and turning. After curing, the segments are carefully removed from the molds and prepared for storage. The mold is opened with precision to avoid damaging the segment. Molds are usually designed for easy dismantling to facilitate this process. A vacuum lifter is used to lift the segment out of the mold, minimizing physical contact to prevent cracks or surface blemishes. Transport to the pre-storage. Segments are transported to a pre-storage area, where they remain until they undergo final inspections. Some segments may need to be turned to ensure they are oriented correctly for the next stages of inspection and storage. Segment storage. Once the segments pass all quality checks, they are transported to the storage area, ready for transport to the tunneling site. The robotization of tubular steel arch installation represents a significant advancement in tunnel support systems, crucial for stabilizing excavations in both soft and hard ground. The automation of these processes offers immediate and effective primary support, enhancing worker safety and mitigating the risks associated with traditional manual installations, particularly in environments where heavy machinery and limited visibility can pose hazards. Macrete Tunneling's semi-automatic tubular steel arch system, in partnership with CP Technology, introduces a specialized handler equipped with a 3-arm mechanism. This handler automates the delivery and positioning of pre-assembled tubular steel ribs, which are transported in a folded configuration to the tunnel face. The automated process involves the center arm positioning the rib's main tubular section, while 2 side arms handle the lateral components. Once in place, pre-installed bracing elements in the ribs secure each segment to the adjacent rib, ensuring precise alignment and stability. The final step involves filling the rib with concrete for enhanced structural integrity. This method minimizes the need for direct human intervention, reducing exposure to the risks associated with manual installations, including falls, restricted visibility, and prolonged exposure to noise. Worker safety is further improved through remote-controlled operations, allowing operators to manage the positioning of each rib without entering hazardous zones. The Safety Track topographic system integrated into this approach provides real-time 3D georeferencing, enabling operators to align and position ribs with precision according to project specifications. A connected display shows the exact rib placement relative to the design model, guiding operators through the process. Data captured on each rib's final position is then wirelessly transmitted to a central computer, where it updates the project's Building Information Model (BIM), providing a digital record of daily progress and quality control. Segmental prefabrication technology represents a recent innovation in prefabricated cantilever bridge construction, bringing new efficiencies and design flexibility to the field. Employed predominantly for bridge structures, it is especially useful in both continuous and simply supported designs, enhancing the speed and quality of construction while minimizing site space requirements. Key advantages of segmental prefabrication technology. This prefabrication method streamlines several aspects of traditional construction by allowing for the rapid assembly of beam segments in a controlled environment. The advantages include high-quality concrete finishes, precision in dimension and alignment, and less reliance on extensive construction sites and equipment. Additionally, the technology enables the construction of porous structures, accelerates timelines, and eliminates the need for traffic enclosures or temporary supporting brackets, enhancing both operational efficiency and safety. Shandong developed a segmental beam formwork system with a high level of structural strength, stiffness, and stability. This robust design endures various construction loads, ensuring that the formwork remains durable and capable throughout the construction process. The surface of the formwork is designed to be smooth and leak-proof, producing tight joints that maintain the intended structure shape and dimensions accurately. Formwork structure and assembly components. The formwork system consists of several parts. Bottom mold assembly. Each pedestal includes 3 bottom molds, a supporting platform, and a trolley. These components enable movement and positioning of segments during assembly and maintenance. The bottom mold trolley features 4 hydraulic jacks, vertical and horizontal, allowing precise adjustments to the horizontal and vertical alignment of beam sections. Side mold and support system. The side mold is attached to the support structure using threaded rods and rotating hinges, making it adjustable to accommodate various cavity sizes in the segmented structure. Internal mold assembly. This mold is designed as a modular unit, customized according to each segment's specifications. Attached to a sliding beam and equipped with a hydraulic system, the internal mold can expand vertically and fold horizontally. A trolley assists in moving the internal mold, simplifying positioning with automated alignment that achieves high precision. Precision and automation. The formwork system's precision is one of its standout features. With 3-way alignment capabilities, accuracy reaches plus or minus 1 millimeter, a critical factor in constructing stable, load-bearing structures. The hydraulic systems facilitate easy adjustments, allowing the internal mold to accommodate both straight and curved sections. This flexibility in segment dimensions means that the system can handle variations in length and section, making it suitable for diverse project requirements. Step-by-step process in segmental construction. Installation and alignment. The formwork is initially set up and aligned, with adjustments made to ensure accuracy in dimensions. Rebar installation and concrete pouring. Rebars are installed within the formwork, followed by concrete pouring. Formwork removal. Once the concrete has cured, the formwork is dismantled sequentially: bulkhead, internal, and side molds. Prefabrication of additional segments. When prefabricating the next segment, the previous segment is used as a reference point, maintaining consistent alignment. This process repeats until all segments are prefabricated. Korean railway construction technology has advanced significantly, driven by a commitment to efficiency, precision, and environmental sustainability. South Korea has developed some of the fastest rail networks in the world, including the Korean Train Express, KTX, which operates at speeds up to 300 km per hour, 186 miles per hour, on standard routes, and up to 305 km per hour, 189 miles per hour, on specific high-speed segments. The network extends over 1,200 kilometers, primarily between major cities, connecting Seoul, Daejeon, Daegu, and Busan with other key regions, drastically reducing travel times and enhancing the national transport infrastructure. The construction of South Korean railways emphasizes rapid deployment with advanced tunneling and bridge building techniques. Tunnel boring machines, TBMs, capable of excavating between 15 to 30 meters of tunnel per day, are frequently used in mountainous areas, helping reduce construction times and costs. The double-track systems commonly employed allow higher traffic capacity, with over 2,000 trains running per day across the KTX network alone, showcasing high operational efficiency. Moreover, Korea's railway technology prioritizes safety and durability. High-performance concrete and advanced steel are used in bridge and track construction, improving longevity and resistance to the region's seismic activities. The Korean Rail Network Authority mandates regular maintenance and upgrades on its infrastructure, including automated track inspection systems that use AI and IoT to detect and address potential issues before they become critical. These systems are reportedly 20% more effective in identifying track anomalies, which has significantly decreased derailment incidents. In terms of environmental impact, South Korea is moving towards eco-friendly railway construction. Electrification of railways has been implemented on over 85% of the network, substantially reducing greenhouse gas emissions compared to diesel engines. The country also actively integrates noise barriers, green zones, and energy-efficient lighting on railways. In some cases, solar panels are installed on sound barriers or stations to reduce power dependency. The Public Transport Authority, PTA, recently completed a major rail infrastructure upgrade in Basundin as part of its turnout, points, and crossing upgrade program. This project replaced old timber bearers and turnouts with more durable concrete, utilizing advanced PEM, point-end machine, and LEM, lock-end machine, technology to enhance the longevity and efficiency of the rail components. With this upgrade, the new concrete bearers are expected to last up to 50 years, significantly extending the infrastructure's lifespan. A key goal of the upgrade was to reduce noise for residents. By installing a more modern crossing system, the PTA has managed to lessen the clatter and vibration often heard when trains pass over turnouts, thereby improving the local sound environment. The project's focus on safety, budget, and timely delivery meant meticulous planning and execution, with on-site management ensuring minimal disruption to train schedules and commuter convenience. Remote-controlled equipment allowed workers to avoid direct interaction with high-risk areas, reducing the potential for injuries and expediting the construction process. Innovative tools also saved time, with a reduction of up to 2 days in welding and installation tasks. The Honam High-Speed Rail Train manufacturing process was developed to meet the demands of Korea's expanding high-speed rail network, specifically for the Honam region. Completed many years ago, this project marked the introduction of a new generation of high-speed trains with enhanced comfort, safety, and advanced technology. A commemorative event was held to celebrate the completion of the first train set, highlighting key innovations in the production process and the high standards achieved in quality control and testing. The manufacturing of the Honam high-speed trains involved a complex and highly automated production process. Each train car was designed with a focus on passenger comfort and operational reliability. This process integrated a modular approach, where each component of the train, from the car body to the interior systems, was manufactured separately before final assembly. This modular setup ensured that each component was subjected to rigorous testing and could be maintained or upgraded individually, allowing for high operational efficiency. Key aspects of the Honam high-speed train included safety systems tailored to high-speed operations. Engineers implemented continuous monitoring systems throughout the trains, providing real-time diagnostics that can alert operators to any operational anomalies. This proactive approach to maintenance and safety ensures minimal downtime and reliable service for passengers. Additionally, Comfort enhancements such as noise reduction and improved seating were prioritized to make long-distance journeys more pleasant. The commemorative event also served as a platform for industry stakeholders to discuss future developments and continuous improvements in Korea's high-speed rail technology. Engineers and industry leaders emphasized the importance of maintaining competitive manufacturing standards on a global scale, working towards technical innovation and excellence. Discussions highlighted the importance of environmental testing and simulation for the vehicles to withstand varying climate conditions across the regions they serve. Moreover, advanced monitoring technology and communication systems were integrated, enhancing both the passenger experience and operational efficiency. The Cugira floating dock is key to expanding the port of Barcelona's pier efficiently and sustainably. With dimensions of 41.3 by 18.5 by 17.5 meters, Cugira enables rapid construction of concrete caissons used to extend the quay. Each caisson is produced in just 8 days, involving a team of 200 workers, enabling up to 160 meters of dock extension per month. In this part, we will learn about the full construction process of the Cebu Bridge in the Philippines. The bridge is built by Acciona and it is one of the most emblematic bridges in the Philippines. The in-situ concrete piles, which support the pillars of the bridge under the water, go down to a depth of 60 meters. They were built with the help of pontoons and vessels, which administered the cementing with a minimal impact on the seabed in the face of strong tides and the channel current. Construction of the road on the bridge, or beam, was done in segments of 7.15 meters, concreted in situ, by moving forward the formwork with its support in the previously hardened section and later concreting. A process requiring a precise study of structural behavior and geometric calculations. For the in-situ launch of the beam in concrete segments or sections, special formwork carriages, executing through progressive cantilevers, were used. The formwork carriages were launched, reinforced with steel and filled with concrete pumped from an area next to the pylons. Once a section was hard, the carriage advanced to complete the next one. The Cebu Bridge towers have 14 guy cables connecting the pylon with the beam to compensate for the effects of strong winds and rain. A total of 56 stays not only give the bridge firmness but also a special architectural effect. Most of China's high-speed trains operate on elevated tracks, maximizing ground space and providing a stable, smooth ride. As high-speed railway networks rapidly expand, China has developed an efficient system for constructing railway bridges to meet growing demand. These bridges are primarily built with box girders, which are large components crafted from structural steel and pre-stressed concrete. Pre-engineered and prefabricated off-site, box girders undergo a rigorous production process involving 9 stages and 18 procedures. This highly structured process, spanning 42 days, transforms raw materials into finished girders weighing up to 1,000 tons each. These robust structures are designed to withstand extreme conditions, such as intense winds, water intrusion, high temperatures, and freezing cold. After production, the girders are transported and assembled on site, where they are bolted together to form a strong foundation for the railway bridges. This approach not only speeds up construction but also improves quality control, ensuring the durability and stability essential for high-speed rail operations. China Railway Construction Corporation on November 3rd released a video of the world's first kiloton bridge girder erection machine. The machine, 40 meters in length and over 1,000 tons in weight, has been put into use to build the Meizhou Bay Cross Sea Bridge of Fuzhou Xiamen High-Speed Railway in southeast China's Fujian province. This China's first kiloton bridge girder erection machine has been deployed in Fujian province for constructing the Meizhou Bay Cross Sea Bridge on the Fuzhou Xiamen High-Speed Railway. At 40 meters long and over 1,000 tons, the machine plays a crucial role in this project. This part is about installing a new underbridge on the main Dublin to Cork railway line at Osberstown, Kildare County, Ireland. The underbridge was constructed in sections beside the rail line over previous months by contractors Sisk and Iron Rod Aran. Several months of preparatory piling works were carried out in the lead up to the possession. To ensure the works could be completed within the tight possession window, a large amount of soil and rock was excavated by excavators and loaded onto trucks in a short time. Byrne Luby were appointed as specialist consultants to design the embedded secant pile wall on behalf of Murphy Ground Engineering. The pile wall consisted of 1,200 millimeters diameter piles in a traditional secant arrangement installed using board piling techniques. The secant pile wall was designed to cantilever for an excavation depth of up to 8 meters to facilitate the construction of the underbridge. The approach walls were installed during normal working hours, with the lengths crossing the railway line installed during shorter nighttime possessions in the lead up to the main possession. Given the limited time frame to complete the excavation and underbridge installation, it was imperative that the design of the secant pile wall and associated temporary works were sufficiently robust, with detailed sequences and methods identified prior to the works commencing. This involved rigorous planning and a series of design and construction workshops with the extended construction team. Heavy-duty cranes lift concrete blocks one by one and place them into position according to the design. Adjustment of concrete blocks into their correct position is facilitated by specially equipped excavators as part of the R407 Salins bypass. A new underbridge was required at Osberstown, on the main Dublin to Cork railway line. The installation of the precast underbridge structure was completed over a 78-hour rail possession during Easter. Iron Rod Aran worked in close collaboration with the contractors and Irish Rail to ensure successful completion of the scheme. Video shows the construction of a 15-meter span Macrete FlexiArch road bridge in Shropshire, England. The patented FlexiArch bridge system is a flat-pack, precast concrete design which replicates the principles of the masonry arch bridge.
The bridge is built from 6 flexible arch ring units. Each unit is made up of 35 tapered precast blocks.
The Macrete FlexiArch can be made for spans from 3 meters to 15 meters with the possibility of wider spans using multiple arches.
This lets the arch ring fall into shape as it's lifted from the transporter. The arch rings can be made to form spans from as little as 3 meters up to 15 meters, with longer spans, skew spans and double arch radius spans in the future. These arch ring units
The Macrete FlexiArch is the invention of Professor Adrian Long, Queen's University, Belfast. Macrete Limited is the commercial development partner.
The load capacity of this bridge is designed for full Highways Authority loading in accordance with BD 37/01. The permitted traffic speed on this B road is 50 miles per hour. Installed on pre-prepared mass concrete foundations with Macrete precast FlexiArch springing blocks, the arch and spandrel construction was carried out through one afternoon. Later, the arch will be backfilled to road level with poured concrete and finished with black top. The spandrels will be
투어신 분들 많겠지만 따끈따끈한 볼거리들로 준비해왔으니 함께 보시죠.